Welcome to the webinar, Finding the Right Fit for Vehicle to Grid. My name is Jessica Hernandez, analyst here at Lux Research, and I will be moderating today's session. Presenting today is my colleague Camilo Cortez, Senior Research Associate here at Lux. Throughout the webinar, you can type any questions you have in the questions box on your screen, and time permitting, we will answer all the questions that we can. If your question does not get answered, please do not hesitate to email it to questions@luxresearchinc.com and we will respond. With that said, let's jump into the presentation.
Thank you, Jessica. So today, we will be discussing one of the technologies that are going to play a crucial role in the future power grid, flexibility. Electric vehicles hold an untapped storage potential for utilities, but unlocking it requires establishing a strong partnership network with different players and offering the right incentives to customers. Until a few years ago, the space seemed very immature thanks to the low adoption of the technology from automakers. However, in the past 2 years, a lot has changed, and multiple projects have sparked around the world. Even automakers like Tesla, who were very reluctant to implement the technology, already offer a vehicle-to-home capable vehicle, the Tesla Cybertruck. But it's not only Tesla. Other automakers like Nissan, Honda, Ford, Volvo, Renault, GM, and BMW, just to mention a few, have already started trials testing the V2G capabilities, and charger OEMs like Wallbox and Siemens already offer commercial-capable vehicle-to-grid chargers. So today, we will be first discussing the importance of vehicle-to-grid. Next, we will understand the key applications and services to implement vehicle-to-grid, and we will close by highlighting the main challenges that need to be addressed in order to achieve commercialization. So I would like to begin by describing the impact that EV charging can have on the peak electricity demand. If we look at the picture on the right, it shows the expected peak demand during winter times presented in the 2022 Future Energy Scenarios report. We can see how if EV charging is not controlled, the peak demand can reach a maximum of 25 gigawatts in 2040. This is something that grid operators and utilities will possibly not be able to handle without upgrading the grid infrastructure. Now, if we observe how the peak demand changes when we control EV charging through smart charging, what we can see is how the peak demand significantly drops by approximately 15 gigawatts. So smart charging introduces flexibility in the system by optimizing the charging process in response to electricity prices or grid conditions. For example, when prices are high or the grid is congested, charging can be slowed or postponed. But although this is a good fit, or this is good for the power grid because it reduces the peak demand, if we further unlock the additional capacity stored in the electric vehicle batteries through vehicle-to-grid, the peak demand becomes negative. What this means is that the combination of smart charging and vehicle-to-grid can not only provide 15 gigawatts of flexible demand, but it additionally unlocks 10 gigawatts of power injection capacity, which could be used to help meeting other types of demand. In other words, vehicle-to-grid can help to defer the construction of additional peaker power plants, which are specially built, as the name suggests, to supply electricity during peak periods. Additionally, according to the National Grid Energy System Operator, unlocking 10 gigawatts of flexible capacity can translate into up to 5 billion in savings on network reinforcements. So today it is clear that many utilities have integrated smart charging in demand response projects aimed at shedding load, but unlocking the additional capacity from vehicle-to-grid requires utilities to provide adequate incentives to customers to build a strong relationship, and in addition, understanding the different types of services and applications through which vehicle-to-grid can be monetized. So 5 years ago, most pilot projects involved providing frequency regulation services, but now we can see how, thanks to the big variation in the type of EVs, duty cycles, and ownership, spark multiple scenarios and services through which vehicle-to-grid can be monetized. Therefore, choosing the right combination of services and applications requires assessing the drivers and barriers that are steering these new opportunities that vehicle-to-grid creates. So before we dive into the different drivers and barriers for vehicle-to-grid adoption, it is important to note that as a utility, you can navigate this space alone, and establishing relationships with software and hardware developers and automakers is key. So each participant plays an important role, and it's like a symbiotic relationship in which all of them are required to thrive. For example, Utilities will win additional flexible capacity that can be used during grid emergency conditions or to meet peak demand, avoiding the construction of peaker power plants. Automakers will gain knowledge of the energy space, opening new possibilities to generate new revenue streams. Software developers could earn part of the generated revenues, and using vehicle to grid, they could program new optimization algorithms that can be developed in order to optimize energy bill reduction or generate new revenue stream. And last but not least, today there are only a few commercial electric vehicle chargers that support the V2G capability. Thus, charger OEMs will benefit from establishing partnerships with automakers as it will open the doors to commercialize their systems. So now that we understand the key partnerships, we also need to comprehend what are the key motivations that EV owners see to adopt vehicle to grid, because unlocking the value of V2G requires building a relationship with the customers. So to evaluate this, we first identified 3 key questions and discussed them with the stakeholders in the V2G space, including utilities, V2G software developers, automotive OEMs, and pilot project operators. So the 3 key questions were: first, which type of vehicle owners are best positioned to adopt vehicle to grid? Second, what are the factors defining whether an application is a good fit for vehicle to grid? And third, what are the main barriers that hinder V2G adoption and how they're strong will their effects be? So to answer the first question, we first look at the type of vehicles and split them into 2 categories, namely light and medium duty and heavy duty vehicles. So for light and medium duty EVs, we consider privately owned vehicles, which can be charged at home or at work. On-site fleets, which these are vehicles owned by a military base, municipality, or university campus, where cars are made available to employees. And we consider service delivery fleets, which includes fleets that leave a central location to deliver goods or provide services, such as a grocery delivery fleet or a last mile courier. On the heavy duty side, we looked at school buses and municipal bus fleets, which are owned by operators of municipal bus fleets servicing urban areas like bus rapid transit fleets. So it is clear that the different vehicle types have varying battery sizes and utilize different charger capacities. And these variables played a very important role when we were doing the analysis. So next, we also look at the type of services that could be provided through vehicle to grid, and we split them into behind the meter and front of the meter. So for behind the meter services, we evaluated backup power, which includes making capacity available for backup power in case of a grid outage. And it is vital to note that outage durations can diverge significantly regionally. For example, in places like the US, blackouts last on average 7 hours, while in Germany and the UK, blackouts generally last less than 1 hour. And the next service that we evaluated in behind the meter was demand charge reduction, which is basically making capacity available for peak shaving on site to reduce demand charges on electricity bills. And for the front of the meter services, we look at frequency regulation, congestion management, which includes making capacity available to reduce peak demand and provide additional energy during peak times or critical grid conditions, like with the emergency load reduction program in California. And last, we have energy arbitrage, which includes charging at low prices and discharging at high prices. So to answer the second and third question, we use the input for the interviews and combine it with our existing understanding of the automotive industry and electricity grid. We identified drivers and barriers to the adoption of vehicle to grid from the perspective of an EV owner, and using a combination of the previously described services and application, we identified the best application and service fit using a weighted scoring system. So the main driver to adopt vehicle to grid is the ability to generate additional revenue. And this amount of revenue can be generated, it can be split into 3 detailed variables, and these are: first, the operational fit, which evaluates how well the service provided matches to the use of the vehicles as an energy resource compared to when it's used for regular mobility-related operations. Next, frequency of the events, which is depending on the type of service provided, V2G can be provided over a different number of hours. Next, we have the capacity offered, which accounts for the fleet size and aggregated capacity that can be available to provide vehicle to grid services. And finally, as an additional driver, we consider the pilot project momentum, which the score reflects the total number of pilot projects currently implementing the combination of application and service. And on the barrier side, we identified 4 key parameters. First, we noted battery degradation, which depending on the service provided, the battery would be subjected to a different type of thermal or cycling stress. Next, we have the regulatory aspects, which the score reflects on how open the electricity markets are to enable participation depending on the type of service provided. So this variable plays a really important role when evaluating front of the meter services. And next, we have the infrastructure cost, which accounts for how adverse a participant will be toward the upfront costs of B2G charging stations and the required grid infrastructure upgrades to accommodate the charging stations. And last, we consider the impact of an interruption, which captures the risk of an unforeseen event requiring the participant to disconnect from the charger unexpectedly. And we look at how the approximate cost incurred for failing to provide the service and perceived impact for the EV owners. So to evaluate this, we scored each factor that drives vehicle to grid on a scale from 1 to 5, where a score of 1 represents a weakly positive impact on B2G adoption, and a score of 5 indicates a very positive impact on B2G adoption. We do the same for the barriers, using a scale from -1 to -5, where a score of -5 indicates a very negative impact on vehicle to grid adoption. So today we will be focusing on the best applications for vehicle to grid, and we are going to start with privately owned light and medium duty vehicles that are being charged at home. So what we see is that despite having the lowest frequency of the events scored, the high number of parked hours of domestic electric vehicles have, the zero regulatory barriers, and the limited need for vehicle visibility make backup power the best fit for charging at home. Similarly, demand charge reduction presents a good fit. However, it translates into higher battery degradation and requires having higher visibility into scheduling vehicles and reducing demand charges to match park time with the peak electricity consumption hours. It is important to note that demand charge reduction is typically applied to commercial and industrial customers. However, there are a few utilities trying to implement this in the US in the residential sector. Last, energy arbitrage, frequency regulation, and congestion management do not present a good fit for charging at home. These services require aggregating minimum capacities to enable market participation, which increases the complexity in using residential bidirectional EV chargers, and needs having visibility into the vehicle availability to schedule market participation and avoid costs by not complying with the offered capacity. So in the UK, we actually have the first commercial vehicle to grid tariff offered to the residential customers through the Octopus Power Pack. So this comes after the Power Loop pilot project performed by Octopus Energy, Nissan, Wallbox between 2018 and 2022. And 2 years after completing the trial, Octopus announced the Octopus Power Pack tariff, which offers free EV charging to residential customers. Some of the key conditions customers need to accept by enrolling include plugging in their vehicles for at least 6 hours daily and charging less than 333 kilowatt hours per month. So the type of grid services that Octopus Energy provides with the vehicles are undisclosed, but this is very relevant. But in addition, Octopus mandates a minimum vehicle time that the vehicle should be plugged, reducing the risk of an interruption. And it is also important to note that the UK electricity market is very open to enable DR market participation, and thus makes providing services like frequency regulation or congestion management a perfect fit, thanks to the reduced regulatory barriers. Next, we have on-site fleets. So typically, this location requires similar charging infrastructure as domestic settings. And according to the US Department of Energy, on average, 8 charging points are installed per location. We assume a ratio of 1 to 2 of vehicles to chargers and fleets of 16 EVs. So this vehicle type is actually one of the best candidates for vehicle to grid, thanks to the high scheduling visibility combined with the low hardware costs. So for frequency regulation, these have a higher impact on battery life and require meeting capacities of 1 megawatt to enable market participation, which could be a big barrier. But on the flip side, frequency regulation generates the largest revenue from all of the analyzed front of the meter services. Next, we can see that backup power and demand charge reduction are the best fit for on-site fleets, thanks to the longer downtime compared to service delivery fleets and not requiring charging equipment with high power ratings, significantly reducing the total costs. Finally, or next, we have congestion management, which requires meeting a lower aggregated capacity compared to frequency regulation, which could ease market participation, but having a lower frequency of the events could result in lower revenues. And finally, we have energy arbitrage, which has similar barriers to frequency regulation and requires having the vehicle parked for longer periods of time, which could significantly impact regular operations, and thus it scores slightly lower than frequency regulation. So one case study involving on-site fleets is the Plymouth State University in New Hampshire, which uses a Nissan Leaf electric vehicle to provide 1 megawatt hour of energy to offset one of the building's electricity needs and reduce its demand charges by participating in a program developed by the New Hampshire Electric Cooperative. And this case study or this project utilized the Fermata Energy charging platform to forecast and analyze day-ahead electricity prices, and then recommendations are sent to the fleet manager to connect and discharge the vehicle batteries at the best times. So now we can move on to the heavy duty category and we can take a look at school buses. So school buses are parked on average 13 hours per day. They have defined schedules and have a larger battery size than light duty vehicles, which makes them a strong application for vehicle to grid. So for front of the meter services like frequency regulation, congestion management, and energy arbitrage, we can see that meeting the minimum aggregated capacity can be easier thanks to the higher rated power chargers that are used, and the larger battery packs could translate into lower battery degradations since they are not subject to a high depth of discharge. However, increased charging power also increases the cost of the charging infrastructure and required site infrastructure upgrades. Next, for front behind the meter services like backup power and demand charge reduction, we can see that the high number of parked hours matching with the typical on-site peak demand and larger battery size makes them a good fit. So overall, school buses are the best application for vehicle to grid. So one case study using school buses is noticed in the US, which in the past 3 years, we have seen high pilot project momentum and the low regulatory barriers, especially in regions like California, where utilities like San Diego and Pacific Gas and Electric, in partnership with Lion Bus and Nuvi, are trialing the capabilities to school buses to help the grid during emergency conditions by participating in the Emergency Load Reduction Program, which provides $2 per kilowatt hour discharge back to the power grid. So now that we have identified the best application and services to provide vehicle to grid, we also need to understand what are the main challenges that are limiting the mass adoption. First, we note that the charging hardware cost is 3 times more expensive compared to traditional level 2 charging hardware, which is typically used at most locations. And second, we need regulations to evolve and remove barriers to enable market access. So this is not only for electric vehicles, but all different types of distributed energy resources. So addressing barriers like minimum market capacity to participate in the market and the type of grid services that can be provided will open new opportunities to monetize EVs. Next to this, speeding up the interconnection approval and simplifying the interconnection request procedure is also required. So the key takeaways from the presentations is that the V2G era is here, and the first main takeaway is that utilities must know the value of establishing partnerships with automakers to understand battery parameters and leverage their data and understanding of vehicle owners. We also need regulations to evolve because although regulations are changing and there are a few leading regions like California and Maryland in the US, standardizing interconnection approval requests and lifting regulatory barriers is key. So leading countries include the UK, where multiple pilot projects have demonstrated the capabilities of DRs to support the power grid. And last, we have to note that utilities need to start, or you need to start pilot projects. So starting with the smart charging programs or offering an incentive tariff is a vital way to collect data and understand how people engage with charging in the residential and commercial settings. While it additionally could help to demonstrate regulators the importance of managing smart charging and unlocking the additional storage capacity that electric vehicles offers.
Thank you, Camilo. We will now be taking questions from the audience that you may have written on the questions box below. So if you didn't throughout the presentation, then you can type them right now. If we do not get to your questions on this call, someone from Lux will be in touch after the webinar. So one of the, I guess, questions, well, like aggregating questions are around costs. So you did mention costs and hardware costs, I think, and regulatory barriers are a key things to tackle for mass adoption. So the question here is, how can costs be reduced in order to enable mass adoption of V2G technologies?
Great, thanks for the question. This is very interesting. So actually one way to address this is by implementing bidirectional AC chargers. So typically DC chargers are used, but AC chargers, automakers and hardware OEMs, they claim that implementing AC, it's much more cheaper and a significant cost reduction can be achieved. But on the flip side, this will require automakers to implement bidirectional inverters on their vehicles. And although this is something that not many automakers have or implemented, a few car companies like Volvo and Renault, they are already trialing this type of bidirectional charging through AC. I hope that answers the question.
I think it does. And during your key takeaways, so I think it was the last point, you call out that utilities should start piloting V2G. You did mention that there have been many pilots already around the world. You mentioned you started with frequency regulation. They have expanded into other use cases and applications. So in your experience, who is the leader of such V2G pilot projects? And what would be the value added for utilities if they are interested in leading such projects?
Sure. So what we typically see is that is the automaker, the ones that is interested in leading the projects. And that's because first, they need to understand the impact of vehicle to grid on the electric vehicle battery. And second, they also want to gain knowledge of the role they can play by entering the energy space, which is a new space for them. So some examples include, for instance, Toyota and Encore, Honda and Nextcraft, which is a virtual power plant aggregator. And we also have Renault and the Mobility House, which Mobility House is a software company that develops B2G software. So yeah, what we see is that mainly the automaker is the one that is leading the pilot projects. And the added value for utilities is basically understanding the new type of products and services that can be offered to customers. So for example, in the Power Loop project, which was performed by Octopus Energy, Nissan, and Wallbox, it basically resulted in the creation of the Octopus Power Pack tariff, which was the one I described on the residential side. So this new product basically offers free electric vehicle charging, but could generate new revenues to monetize EVs by providing grid services. So Octopus Energy could generate new revenues by doing this.
So there are a few things that utilities will get out of participating in such projects. You mentioned the opportunity to create new products and services based on the gained understanding of their customers' needs, wants, and the new types of, in this case, assets, which are electric vehicles that are being adopted, increased visibility also. So there are a few key things, right?
Yep, probably in addition, you could also win additional storage capacity, which is basically free because you don't need to pay for that capacity that is already available in the electric vehicles. It's an additional thing that they could win.
Yeah, definitely. Access to these new distributed energy resources available and that are mobile everywhere. I think we have time for one last question. I know that during your presentation, you focused on 3 of the use cases for V2G, and you evaluated their fit for V2G. But in this case, I know you didn't talk about municipal bus fleets, but you did call out school bus fleets. So they also have large batteries and they have a good scheduling visibility. So why does that application wouldn't be as good as school buses? If not, or if it is, then could you elaborate a bit more?
Sure. So that's a really nice question. And basically, what we can see is that despite these vehicles have a larger fleet size, which could is meeting the minimum aggregated capacity for market participation, these vehicles have a really low downtime, which reduces the total number of parked hours. And in addition, they typically use fast chargers, which could increase the cost significantly. So most municipal bus fleets basically show us that regardless of having a larger battery, fleet size, and high scheduling visibility, demonstrating a good operational fit is key in order to provide vehicle-to-grid services. So basically matching the use case of the vehicles to their original use case, it's really difficult because these vehicles are most of the time en route and they are not parked for long periods of times compared to the other applications or like a school buses, which are typically parked for 13 hours on average.
Right. Yeah, it is a huge difference. I guess also municipal bus fleets will probably be parked overnight, while school buses are plugged during the day when they don't have to pick up and drop off, right? So it's
Correct.
when the services are necessary. All right. Well, thank you very much, Camilo. That concludes our webinar for today. The slide presentation and recording from this webinar will be sent to all attendees via email today. After leaving the webinar, you will be prompted to complete a survey on today's presentation. We would appreciate any feedback you may have to help inform and improve future webinars. Take a moment and check out our upcoming webinars. Thank you very much for joining us and have a great day.